In the early hours of Saturday, August 22nd, a powerful magnitude 6.2 earthquake tore through one of the most remote and least monitored stretches of ocean on the entire planet, the frigid waters of the Scotia Sea, deep in the South Atlantic near the coast of Antarctica. Very few people felt it. Almost nobody was directly in its path. But for scientists tracking seismic activity across some of the planet's most tectonically active boundaries, this quake instantly became a data point worth serious attention, both for what it tells us about this remote corner of the world, and for what it reveals about how modern earthquake monitoring actually works in places almost nobody lives. Stick with me, because this quake is a genuinely fascinating window into an entire hidden layer of geological activity most people never think about. Let's start with the hard numbers. According to the United States Geological Survey, the earthquake struck at Order 8.22 UTC on August 22nd, registering a magnitude of 6.2, with the European Mediterranean Seismological Center independently confirming the exact same magnitude and depth. The quake originated at a remarkably shallow depth of just 10 kilometers, roughly 6.2 miles beneath the seafloor, a depth shallow enough that it's classified by seismologists as a genuinely strong, shallow rupture. Some monitoring services placed the earthquake specifically 113 kilometers west of Coronation Island in Antarctica's South Orkney Islands, while official USGS positioning placed the epicenter within the broader Scotia Sea region, one of the most geologically complex and seismically active stretches of ocean floor anywhere in the southern hemisphere. To understand just how remote this location actually is, consider the nearest population centers. The epicenter sat roughly 1,330 kilometers, or about 827 miles, east-southeast of Tolhuin, a small town in Argentina's Tierra del Fuego province, with a population of only around 3,000 people. It was even farther still from Ushuaia, often described as the southernmost city in the world, and from Rio Grande, another Tierra del Fuego community. In other words, this was a genuinely powerful earthquake occurring so far from any significant human settlement that the overwhelming majority of people on the planet had no possibility of ever feeling its shaking directly, even though the rupture itself released a substantial amount of seismic energy. If you're new here, this channel breaks down the biggest natural disaster and science stories unfolding around the world, so make sure to like this video and subscribe so you catch the next update the moment new seismic activity is detected anywhere on the planet. So why does an earthquake in such an empty, remote stretch of ocean matter at all? The first and most immediate concern anytime a significant earthquake occurs beneath or near an ocean is the possibility of a tsunami. Following this quake, the National Weather Service's Pacific Tsunami Warning Center moved quickly to assess the situation, and based on all available data, officially determined there was no tsunami threat to Caribbean coasts stemming from this event. That assessment matters because it reflects exactly how tsunami warning systems work in practice, evaluating an earthquake's magnitude, depth, and specific fault mechanism within minutes to determine whether the rupture was capable of displacing enough seafloor to generate a genuinely dangerous wave. And in this case, the evidence pointed toward a low-risk outcome for the distant coastlines being monitored. The USGS also assigned this earthquake a green alert level for both shaking-related fatalities and economic losses, the lowest tier on the agency's color-coded alert system. A green alert specifically indicates a low likelihood of any casualties or significant damage resulting from the event, a classification driven largely by the region's near total lack of population rather than any inherent weakness in the earthquake itself. It's worth understanding that alert level on its own doesn't measure how powerful an earthquake was. It measures the practical, real-world consequences based on exactly who and what happened to be sitting in its path. And in this particular case, that path happened to run almost entirely through open ocean. Now, let's talk about what actually makes the Scotia Sea such an active earthquake zone in the first place. Because this region has a genuinely fascinating and somewhat unusual tectonic setup compared to most of the world's other major fault systems. The Scotia Sea sits at the boundary of a small, relatively obscure tectonic plate called the Scotia Plate, sandwiched between the much larger South American Plate to the north and the Antarctic Plate to the south. This entire boundary zone is riddled with a complex mixture of transform faults, where plates slide horizontally past one another, and subduction zones, where one plate dives beneath another, making it one of the more geologically intricate plate boundaries anywhere on Earth, despite receiving a tiny fraction of the scientific and public attention given to more famous fault systems like the San Andreas or the Pacific Ring of Fire's more populated stretches. This region's history of significant seismic activity actually extends back further than many people realize. Records show that a magnitude 7.0 earthquake once struck in the South Atlantic, southwest of the disputed Falkland Islands, following a remarkable sequence of 4 other earthquakes that each measured above magnitude 5.0 within just a 2-hour window leading up to the main event. Seismologists studying that historical sequence noted specifically how uncommon earthquakes of that size are in the broader region, pointing out that only around 15 earthquakes above magnitude 5.0 had been recorded there across the previous 4 decades of monitoring. That kind of rarity underscores just how significant it is whenever a quake in this general area crosses into the magnitude 6 range, as this most recent event did. Interestingly, this wasn't even the only notable earthquake to strike the broader South Atlantic region this year. Earlier in the year, back in January, a very strong magnitude 6.0 earthquake struck near South Georgia and the South Sandwich Islands, another remote island chain within this same general stretch of ocean. That earthquake was followed by several detectable aftershocks over the following weeks, including one reaching magnitude 5.7 roughly 3 weeks after the initial event, a pattern entirely consistent with how larger earthquakes typically behave, generating a decaying sequence of smaller aftershocks in the same general area for days, weeks, or in some cases even months and years afterward as the surrounding crust gradually settles following the initial rupture. There's a broader lesson buried inside stories like this one about how earthquake monitoring actually functions across the entire globe, not just in densely populated, well-studied regions. Modern seismic networks, combining data from the USGS, the European and Mediterranean Seismological Center, and numerous other national and international monitoring agencies, are sensitive enough to detect and precisely locate earthquakes occurring in some of the most isolated stretches of ocean on the planet, often within minutes of the rupture actually occurring. This global coverage exists precisely because seismologists understand that earthquake risk doesn't respect political borders or population density. A major rupture occurring near a heavily populated coastline could just as easily originate from the exact same kind of plate boundary responsible for generating quakes in a nearly empty stretch of the Scotia Sea, which is why continuously monitoring even the most remote corners of the planet remains a genuinely important part of the broader global earthquake and tsunami warning infrastructure. There's also real scientific value in studying earthquakes like this one specifically because of how relatively understudied the Scotia Plate boundary remains compared to more heavily instrumented regions elsewhere in the world. Every additional data point collected from this remote stretch of ocean helps researchers refine their understanding of exactly how the Scotia Plate interacts with its larger neighboring plates, information that feeds directly into broader models used to estimate long-term earthquake and tsunami risk, not just for this specific region, but for similarly complex multi-plate boundary zones found elsewhere around the globe. In that sense, even an earthquake that harmed no one and made barely a ripple in mainstream news coverage still contributes meaningfully to the much larger, ongoing scientific effort to understand how our planet's crust actually behaves along its most complicated fracture zones. It's also worth understanding the mechanics of exactly why an earthquake this shallow tends to attract closer scientific scrutiny than considerably less distance to travel before reaching the surface, or in this case, the seafloor, compared to earthquakes originating 50, 100, or even several hundred kilometers deep. That shallow origin generally means the energy is less dampened by the time it reaches the seafloor above it, which is part of why shallow earthquakes carry a proportionally higher tsunami risk for any given magnitude compared to their deeper counterparts, even when, as in this specific case, the final assessment determined the actual threat to distant coastlines remained low. The specific fault mechanism behind this earthquake also matters considerably for understanding why it did not generate a significant tsunami despite its shallow depth. Tsunamis are primarily generated by vertical seafloor displacement, the kind of up and down motion typically associated with thrust faulting along subduction zones, where one tectonic plate is forced beneath another. Many of the fault systems within the Scotia Plate boundary, however, involve significant strike-slip motion, where the plates grind horizontally past one another rather than one plate thrusting vertically beneath its neighbor. That horizontal style of movement tends to displace far less water vertically compared to a thrust event of similar magnitude, which is a major reason why an earthquake of this size in this particular tectonic setting was assessed as posing minimal tsunami risk to distant shorelines. Antarctic and sub-Antarctic seismic activity in general receives comparatively little sustained public attention, largely because the entire region hosts so few permanent human residents compared to virtually anywhere else on the planet. But that lack of population doesn't mean the region lacks scientific importance. Research stations scattered across Antarctica and nearby island territories, along with a network of ocean bottom seismometers and satellite-based monitoring systems, continue collecting valuable data on how this remote, complex junction of tectonic plates behaves over time. Much of what scientists currently understand about the Scotia Plate's boundaries and movement patterns has been pieced together gradually, earthquake by earthquake, using exactly this kind of continuous, patient monitoring rather than any single dramatic breakthrough event. There's also an important distinction worth drawing between this earthquake and the kind of major damage-causing events that tend to dominate international headlines. Earthquakes striking directly beneath or near densely populated coastal cities, regardless of magnitude, carry an entirely different risk profile than one occurring in the middle of the open ocean, hundreds of miles from the nearest small town. This magnitude 6.2 event released a genuinely significant amount of seismic energy, comparable in scale to earthquakes that have caused considerable damage and loss of life in more populated regions around the world. Yet in this specific case, the sheer remoteness of the epicenter meant the practical human impact remained effectively negligible. That contrast is a useful reminder that an earthquake's true danger depends just as much on where it strikes as it does on how powerful the underlying rupture actually was. This event also fits into a broader pattern worth keeping in mind. The sheer volume of earthquake activity happening across the planet at any given moment, the vast majority of it entirely unnoticed by the general public. Global monitoring networks routinely detect dozens of earthquakes above magnitude 2 within the South Atlantic region alone across any given week, with the overwhelming majority far too small or far too remote to ever make headlines. A magnitude 6.2 rupture like this one stands out specifically because it crosses a threshold seismologists generally consider strong enough to warrant closer, more detailed analysis, triggering the kind of rapid cross-agency assessment process, tsunami risk evaluation, alert level classification, and aftershock monitoring that quietly plays out every time an earthquake of this scale occurs anywhere on Earth, whether or not a single person happens to be close enough to actually feel it. Before you go, if this kind of deep dive into the seismic forces shaping our planet matters to you, hit subscribe so you catch the next. Update the moment a new significant earthquake is detected anywhere in the world. Because as this event shows, even the planet's most remote, empty stretches of ocean floor are constantly being watched, measured, and studied by scientists working to understand exactly what's happening beneath the waves. Thank you for watching, and I will see you in the next one.